Welcome to EDU World Space.
Okay, in this question, you have a puck and you're pulling it on a court. It's rotating and you're pulling it, and you want to know some things about the speed at the smaller radius, the tension, and then how much work is done. So let's write down the givens and discuss how to do the problem. The mass is 50 grams. Let's write that in kilograms. So 0.050 kilograms. And the initial velocity is 1.5 meters per second. And the R is 0.3 meters. And the final R is 0.1 meters. And first we want to know the speed at the smaller radius. So let's kind of draw this out and make sure, I'm tempted, of course, to use angular momentum conservation, but let's make sure that that makes sense. And then that's legal. So here's the tension. And then if you're pulling on the puck, your force is this way, and then your R is also this way. And so they're going to always be aligned, so then there's no net torque on the puck. So you can use angular momentum conservation. And so so the mass stays the same. So then R is always perpendicular to V. So you can basically just say that V initial R initial is equal to V final R final. And then you can get that the final velocity is equal to V initial times the ratio of R initial over R final. Ooh, can I do this in my head? So that's 1.5, and then initial over final. Oh, did I copy that wrong? Oh no, 0.3 to 0.1. So that's 3. So it's just going to go 3 times 4.5. So 3 times 1.5, which is 4.5 meters per second. And what we want to do then is find the tension in the cord at the smaller radius. So if it's rotating at that constant velocity, we assume we kind of stop at that point. You can say that doing a free body diagram on the puck, the force is inward, and you can use the force as the tension, and then that's equal to mv squared over r. So we want to do 0.5 times this velocity squared divided by 0.1. So, or 0.05, excuse me, 0.05 times 4.5 squared divided by 0.1. And then that's 10.1. Newtons. Let's double check. 1/2. And then we want the work done as it changes its position from 0.3 to 0.1. And so let's see. I think that it makes sense to do this by doing work as the change in kinetic energy. So oops, that was actually B. Here's A, and then now I'm going to do C by evaluating the change in kinetic energy is equal to the work. And then the change in kinetic energy is 1/2 m times V final squared minus V initial squared. So that's going to be 0.5 times 0.05 times 4.5 squared minus 1.5 squared final minus initial. So that's 0.45 joules of work. Oops.